Alright, tonight's lesson is going to be over radioactive particles and decay, which is the first lesson in the nuclear physics module. The first thing that we need to go over are the subatomic particles. If you haven't or are familiar with this, we're just going to quickly review the subatomic particles, which are protons, neutrons, and electrons. Within an atom, there is a part called the nucleus, which is the centermost part of the atom, and it is consisted of or made up of protons and neutrons. The electrons are floating around in electron levels or electron clouds outside of the nucleus. Protons have a positive charge, neutrons have a neutral charge, and electrons have a negative charge. And the number of protons determine the element. And together the protons and neutrons sometimes are referred to as nucleons as well. Information is quickly given about the nucleus of an atom using the nuclear notation. Need access to a periodic table to help you write the nuclear notation. So you can see in the formula below that Z is going to be the number of protons, which is also the atomic number. A is the atomic mass of the specific isotope, never the average atomic mass, and X is the symbol for the element. To find the neutrons, all you're going to have to do is subtract the number of protons from the atomic mass and follow the formula N equals A minus Z. Isotopes are a version of the same element, so they're going to have the same number of protons, but with different numbers of neutrons, resulting in a different mass number. Natural abundance. The natural abundance of an isotope is a number that tells the percent of total sampling of a substance that will be a particle isotope. An example is the isotopes of carbon. The atomic mass units. These are some numbers that you probably would like to write down on your formula sheet or memorize them if you don't use a formula sheet. The mass of atoms and subatomic particles is given in a unified atomic mass units, so it's represented by the unit of a U. So here are the mass of the subatomic particles. The mass of a proton is 1.007276 U's. The mass of a neutron is 1.008665 U's. And the mass of an electron is 0.0005485 U's. Missing the U there. The difference in mass is converted into energy, and we can calculate this using the famous equation from Einstein, E equals mc squared. The total mass of a stable nucleus is always less than the sum of the masses of its separate protons and neutrons. And the difference is the mass is the binding energy, or the energy that is holding the nucleus together. So we can use the mass to determine the energy that holds that nucleus together. So in order to calculate energy, you must know the mass of the subatomic parts to calculate the binding of the energy. So the mass, here's an example. So the mass of the atom of helium-4 is 4.002603 U's. To calculate the binding energy, we must calculate the mass of the parts. So we know that helium has 2 protons, 2 neutrons, and 2 electrons. So we add those together, so 2 times the mass of the protons plus 2 times the mass of neutrons plus 2 times the mass of electrons. So the total mass is 4.03297916 U's. Now you subtract the total mass of the parts from the mass of the atom. So you take 4.03297916 minus 4.002603 U's, and you should get 0.0303761 U's. It is important to round all the way out. So now we take that mass and we're going to convert it into energy. So we have that 0.0303776 U. And we have to know that 1.0 U's of mass has 931 MeVs of energy. So 1.0 EVs is the energy stroked by moving one electron across 1 V's of potential difference. So in other words, you're going to have to know the number 1.602 times 10 to the negative 19th of energy. So we're going to use this equation below to determine the energy in the atom. So we plug in what we have, 931 times 10 to the 6 EVs over the equation, and we should get 1.49 times 10 to the negative 10th joules. So then we take the mass of what we calculated from the first part of the problem, 0.030376 times what we just calculated, 1.49 times 10 to the negative 10th, and we should get 4.53 times 10 to the negative 12th joules. Now we're moving on to the topic of decay. The binding energy is the energy needed to break apart the nucleus. To be a stable nucleus, the mass must be less than the sum of the parts so that there is positive binding energy. If the binding energy is insufficient, then the isotope will undergo something called radioactive decay. And in 1896, Henry, I can't pronounce his last name, discovered that uranium would darken photographic plates. This led to the discovery of radioactive decay, or an unstable nuclei falling apart and emitting certain types of radioactive particles or energy. Just on the side note, if you're a history buff, the atomic bomb, this is the release of a lot of these atoms or nuclei splitting apart and releasing that form of energy to create that massive explosion. So there are actually 3 different types of radioactive decay. We have alpha decay, beta decay, and gamma rays. So we're going to talk about these a little bit more in detail. Alpha decay, which can be stopped by just a simple sheet of paper. An alpha particle is a helium nucleus, and when an atom undergoes alpha decay, it loses 2 protons and 2 neutrons. An example of alpha decay is the decay of radium-226 to radon-222. So you can see in the formula below, that's how you show alpha decay, changing from radium over here 226 to radon-222. So you're going to have that 1 helium atom. Transmutation. You have a parent nucleus, which is the original, a daughter nucleus, which is the nucleus of the new atom created, and the transmutation is the change of one element into another. So the basic form of alpha decay can be followed by the formula that you see on the page right here. Oops. The alpha particle is ejected because it has a very large binding energy and is difficult to break apart. Now moving on to beta decay, the second type. The mass number stays the same and the atomic number changes by 1. So a beta particle, B negative, is an electron emitted by the decay of a neutron. The result of the decay is that a neutron becomes a proton. This occurs in the decay of carbon-14 to nitrogen-14. So you can see here the carbon is going to change to nitrogen because it's going to be giving off an electron. So the general pattern for that formula can be seen at the bottom of the page. Gamma rays are just very high energy photons. They occur when a nucleus is in an excited state. So just like electrons when they have moved to higher energy levels. When it drops down, it emits a gamma ray. The excited state occurs from other 2 types of decay. This energy is much higher than the typical photon emitted by the electron changes. For a given decay, the gamma has the same energy. So the typical equation for the release of a gamma ray can be seen on the formula on the bottom of the page. This symbol is represented with that gamma ray, that photon. So a decay series shows the actual progression of radioactive decay starting with a particular element. For example, the first 4 decays of uranium are shown below. So you have uranium-238 and the alpha, and then you have 2 decays of beta, again all the way down. That's how you follow the progression of the decay series. All right, now moving on to the practice problems. The first practice problem says calculate carbon-14. So it has the mass for carbon is 14.003241. So we know by looking in the periodic table that there are 6 protons, so we're going to take 6 times the mass of a proton, and we should get 6.043656. We know that it has 8 neutrons because we can subtract 6 from 14, so we're going to get 8. 8 times the mass of the neutrons, and we're going to get 8.06932. And then we need to find the electron 6. These two always equal each other. So we know that the atomic number is proton, so it also has 6 electrons. So we have 6 times the mass of the electron, and we're going to get 0.00329148. So after we add the 3 of these together, we should get the total mass of 14.116267. So now we're going to subtract to find the difference in mass. So we subtract what's given to us in the problem from what we calculated, and we should get 0.113026. So now we convert it to energy by using that equation that we talked about. The standard right here, 1.49 times 10 to the negative 10th. And we should get 1.68 times 10 to the negative 11th. The second problem says draw the symbols for thorium-230. So what we need to do is first look at the periodic table. So, and we're looking for TH. I was about to say I can't find it. It's down here. So we see that the atomic number is 90 and the mass is 232.0381. So we have 90, which is the atomic number, and the mass here is given as 230. So lead is symbol is Pb, which is right here in the middle. Pb, that is a Pd. Sorry about that, guys. Hello, Pb, which is lead. I was looking at that going, that is not right. So they have atomic number of 82. So we go P. Oh, can't do the Pb. 82, because that's the atomic number, and we have 210. So write an equation for the alpha decay of polonium 210. So we find the polonium, which is 84 right here, if you didn't have a periodic table. So we take PO 210, 84, and again, remember that you're taking that helium atom for alpha, so that means you're going to subtract 4 from 210, and you get the 206 up here that you see. Let's see if I can get a different color. 206 right here is from subtracting 4 from 210, and then subtracting 2 from 84, we get 82. So if you need to figure out what symbol is 82, you look at your periodic table, and we've already found it, which was lead, Pb, not Pd, and that's how you write that equation. The second part says the beta decay of thallium 206. So we find thallium, which is right here, 81. So we do 206, atomic number is 81. And again, since we're doing beta decay, it's just a loss of an electron. So we do 206. We know it's lead again because we're gaining that electron there. So we add 1. And that's how you write the equation for that beta decay. And that is it for the first lesson in the module. Thanks for watching, and let me know if you have any questions.